In modern physics, there is this quantum mechanics theory. And this particular quantum mechanics theory is related to the notion of uncertainty. And for people who have listened to whatever podcast, lectures, and so on the topic, they are aware that somehow there is a sort of intrinsic uncertainty and therefore probabilities associated to the microscopic world that is allegedly described by quantum mechanics. Now, what is a bit more curious is about probability laws that appear in classical physics. And in fact, that this has been a big puzzle for physicists of the 19th and 20th century, and it still remains a puzzle today. So what I would like to discuss is basically what this is about. So one of the questions that we can ask and that people ask themselves essentially in the 19th century had to do with what is heat. And in particular, heat is going to be represented or measured via the quantity called temperature and also via temperature changes as well. As some of you may know, heat was considered to be initially via the caloric theory from Lavoisier. It was meant to be a sort of fluid which would actually circulate among matter. It was a sort of remnant idea of the fire element, and so essentially this fire kind of liquid would essentially move from one body to another. But of course, later on, some additional conceptualization of heat have come about, and most particularly the kinetic theory of heat and thermodynamics in general. And that's basically what we are going to talk about. So one of the things that you may hear or read basically very, very commonly is basically something along the lines of, heat or temperature is just the average kinetic energy of particles in the system, and there you go. There is nothing really much to be said about it. But upon further introspection, if you think about it, the average of what first, and then the term average seem to correspond to, or at least is attached to, probability theory, is attached to gambling, is attached to stuff like that, which in principle are not quite typical in physics. Essentially, it started, at least one of the most, pioneers in this is James Clerk Maxwell, who in the 1870s, basically proposed that you could conceive temperature as being a single parameter characterizing the entirety of the speed distribution of particles in a system. And then the speed of the particles would be given not by a specific formula, but rather by a probability distribution, which is what I'm displaying here. And what you see is that essentially the smaller, the lower the temperature, expressed here in Kelvin, essentially the narrower the speed distribution is going to be, and of course the sharper is going to be as well. So it's going to change both the width of the distribution, but it's also shifting it toward the left if you decrease the temperature, and of course then towards the right hand side if you increase temperature. And again, this type of distributions, I didn't give any formula here, but these are called Gaussian distributions. So here this is a skewed Gaussian because this is for the speeds that we are looking at, but essentially they are fairly standard, and they are set only by one parameter, which is here the temperature. Now, because there is only one parameter, what that means is that you're going to get that the average speed squared is proportional to the average kinetic energy, and which is itself proportional to the temperature. And therefore it does give rise to this interpretation of temperature, which is just the average of the kinetic energy or the speed squared. Now this particular relation is only one of the many consequences of having the entirety of the distribution being characterized actually by the temperature. So the depth, let's say, of information you can extract from the distribution is way more important than simply knowing the average. And this is conceptually and also quantitatively much more important and interesting. Okay, so that's basically the idea. But the problem with mentioning these ideas of the average kinetic energy is proportional to temperature and so on is basically that it's not clear where these probabilities are coming from. And when you think about it, this particular development started when essentially probability theory started to be developed as well, or at least was very, very kind of new thing that people were using essentially for gambling, and in fact for doing some sort of live versions of what we would call today Monte Carlo experiments. So what do we do then as physicists, where we start talking about probability laws? In particular, as you probably may know, in those days, physics was completely deterministic. You had the laws of Newton that were completely determining, especially with conservative forces, they would be determining the motion of any system. And here I just wrote F equal ma, where I express F for conservative forces as being the minus of the gradient of the potential energy of the particle you're looking at here, for example. Okay, but this is just here just to show you what you would expect. So people were looking at these deterministic laws and they were, okay, why do I need then to talk about probabilities? And so this is essentially what Boltzmann, but he was compelled by Maxwell to look into it, but tried to justify. And the example he found is quite interesting. So here I wrote what is called the Hamiltonian, but you can view that as simply the energy function of the system. And what I'm looking at is simply the kinetic energy here, that's px squared over 2m plus py squared over 2m, and then plus some other terms that are quadratic in x and y. And these terms are nothing but a harmonic oscillator. So it's actually a two-dimensional harmonic oscillator. So what that means that there is a sort of spring, if you will, in both the x and y direction. And it just so happens that the strength of the spring is not the same in the x and in the y directions. Okay, so it's a so-called anisotropic harmonic oscillator. And Boltzmann noted in a paper in 1871 that, well, if you take the ratios of the frequencies omega x over omega y to be rational, then you should observe something like this. Okay, so the trajectory goes on, and here on purpose I took a relatively large ratio between the two, so you're going to see a sort of lengthy kind of curve going back and forth. So this is a sort of oscillation indeed for a harmonic oscillator. But what you are going to see soon enough is that essentially is going back to the same 2 points when you look at the intersection with the y equals 0 axis. Okay, so I'm just highlighting the crossings at the y equals 0 axis here. And so what you're going to see from here, in fact, is that the curve is always the same. So it's following the same curve over and over again, so indicating that it's a periodic orbit. Now, what Boltzmann and many people knew in his times is that basically if you take omega x over omega y to be irrational, then you're actually going to get things that are much more interesting. And in particular, we could get trajectories like this. So here it's in green, and you are going to understand why in a minute. So we see 2 points here again, but as you see, we get more and more points as time goes. So here we've got 4 points already intersecting with the rest, and so on and so forth. So you see that the trajectory seems to spread along the actual kind of plane xy, but let me actually do this here. But also it actually intersects more and more points that are all different along the x-axis for y equals 0. So what that means that for a single value of y, which is 0, you're getting more and more points along the x-axis. And that's actually what Boltzmann and Maxwell called the ergodic hypothesis. And the idea here was that in the long run, the orbit is going, so the orbit here is the trajectory that is in green, is basically going to fill the entirety of the plane. And for example, if I take one value, y equals 0, I will be able to get all possible x values on the real line in this interval, which is from -1 to +1. And so the idea here is that essentially is going to fill the entirety of the square I've got here. Now it was even larger because the idea was to fill so-called phase space, so also you would have the same in the px and py plane, and actually the Cartesian products of all of these things. So that's the main idea. Now, why is it that they actually wanted to do that? Well, this is explained by Paul and Tatiana Renfest in a book they actually wrote, or a long article, it depends how you want to look at it, in 1912, which was on the conceptual foundations of the statistical approach in mechanics. And this, by the way, the 1912 one was written in German, and then it was translated later and accessible in English translation in 1959, so actually quite much later after the original translation. Now, what they actually highlight is the following. So the G path is precisely the actual green curve we've seen earlier. And that's point 1, 2, and 3. And I want you to actually have a better look at point 3. What they say is that all of these motions yield the same value for the time average of any function of the phase variables. So what they want to say is that if you were to take the time average, which can be defined deterministically for any causal signal, then basically they say that this particular, like whatever motion you take, whatever initial state you start from, you're going to actually get the same time average of any function you're looking at. Okay, and so this then gives you a sort of idea that there is an objective, physically meaningful notion of average. Okay, and therefore from this notion of average you can construct equally so a notion of probabilities, or at least relative weights and stuff like that. And that's basically what they were looking for, because Boltzmann and Maxwell had actually put together this idea that we would be looking at various probability distributions here, and therefore this particular universal averaging was incredibly important to justify some a priori probabilities they wanted to put forward. So let's have a look at a critique by Paul and Tatiana Renfest of this particular idea of ergodicity, which I've just mentioned, which is that the curve is eventually going to fill the entirety of the space, regardless of where you start. So here I'm going to continue the actual simulation, running the trajectory further in the future, if you will. So I'm starting from where we left, and then we are going to see essentially this blue curve, which is essentially in the future of the green curve. So what you see is that you continue to obviously intersect the y equals 0 axis at different values, and which are always kind of increasing in number. They can get close or far from existing intersection points. That's perfectly fair enough. But one of the things that we start seeing is that actually it's not really crossing or overlapping with any of the green curve. Okay, and that's what we are going to look at. So what happens is that from this particular, at least for this particular system, we could say that the curve is never going to fill the actual square. And the way we can say that is basically following this particular, let's say, argument. So imagine that you start an initial trajectory from any point on the blue curve, and then you make it move on further in the future. Okay, so you're going to continue plot the blue curve. Fair enough. But if you assume that this blue curve is eventually going to fill the entirety of space, then it should also eventually overlap with any point of the green orbit which is in the past of the blue curve. But if it actually crosses or overlap with any portion of the green curve, then basically it means that it's periodic, okay? Because the blue curve is in the future of the green curve, so if the blue curve is able to come back to some point in the green curve, it indicates periodicity. But the problem is that it turns out that the irrationality of the ratio omega x over omega y in principle prevents any periodicity whatsoever. It's an aperiodic system by construction. Okay, and therefore for this particular situation, which Paul and Tatiana Arendt first considered to be essentially very general, it's impossible to get the ergodicity that was sought for by Maxwell and Boltzmann. Now, of course, what they do themselves is suggest some other things and some of the technique to try to define or a weaker definition of ergodicity. I'm not going to enter into these specific details. What I would like to discuss is something a bit different. Because here the argument relies heavily on the specific example we've used, I think it would be interesting to see whether any kind of general argument couldn't be made about this, and about whether or not you could find some Newtonian trajectory that is actually ergodic in the sense of Maxwell and Boltzmann. And as it turns out, there exists a set of curves, for example, which are called piano and Hilbert curves, but there are some that have been proposed by Lebesgue as well, and these are so-called space-filling curves. They are genuinely curves, so they can be parameterized with some time parameter, if you will, and basically what these curves do is that they actually fill space. So here on the left, I'm representing a so-called piano curve, so that's the first example that was provided formally by Piano of a curve which is basically in R1 that takes basically a parameter, time, for example, and eventually fills the entirety of R2. Okay, so that's actually quite fantastic. And on the right-hand side, then you've got so-called Hilbert curves, which have the same kind of characteristics, but it's just that the curves themselves are slightly different. Now, one of the things you notice is that all of these curves, they have kinks. So they've got this kind of U-turn that are incredibly straight, so they really have actual kinks here and there. And so one of the questions that we could ask is whether Newtonian trajectories, whether they can be space-filling or not. Is there any kind of argument that can be made to say that Newtonian trajectories can be or cannot be essentially space-filling in the way, again, Maxwell and Boltzmann initially thought. And it turns out that this has been answered by a mathematician called Michel Morin, and basically that's in 1987, so that's more than 100 years after these ideas by Boltzmann and Maxwell. And what actually he showed in the paper on differentiability of piano type functions is that that's in the theorem 3 of the paper. It's obviously a little bit complicated in terms of all the words that are there, but what is important for us is that if you want to have essentially a differentiable curve to be space filling, then essentially you can't. That's kind of the bottom line. So if you have a differential curve what you're going to find if you actually make it go through R2 is that it's not going to go through all points in R2, and in fact it's going to go, basically infinitely many points are missing there. That's the idea. And so the conclusion from that is that no differential curve can be space filling. Now you could say, okay, what's the point here about no differential curve? Well, we've seen earlier essentially F equal ma, okay? And the acceleration here is the second derivative of the position. So essentially, if you want your position, acceleration, and velocities to be defined and not be blowing up or being infinite, then you need to have the curves to be differentiable. And because actually this is impossible, it follows that Newtonian, like the curves generated by following Newtonian mechanics, cannot be space filling in general. And that of course applies for any extension, let's say, of Newtonian mechanics, that would be Lagrangian mechanics or Hamiltonian mechanics. So that's kind of the bottom line. We cannot have actually ergodicity basically in any kind of dynamical system with kind of differentiation and differentiable curves. So then you could say, okay, so where does that leave us? Well, that's kind of the problem, to be honest, is that as far as I'm aware, this is still a very much open problem. First of all, ergodicity itself is an open problem, so there are still people trying to define, and I'm actually one of them, trying to define ergodicity, trying to measure ergodicity in some systems, but it's not clear whether this particular property is going to be necessarily the property to explain and conceptualize why do we use probabilities for classical physical laws. And then of course there are various programs that exist and various solutions that have been proposed, like for example a connection between information and thermodynamics, but that would be for a different day. Okay, so I hope you enjoyed this excursion into probabilities, classical mechanics, and a bit of mathematics and measure theory. And with this, please leave any comments in the comment section below, and see you next time.